Dear students, already we have covered the different properties of matter, one and different elastic constants, what is Young's modulus, rigidity modulus, and the bulk modulus, and what are the relation between the elastic constants, Q, the Young's modulus, N, the rigidity modulus, and K, the bulk modulus in the last class. In this class, we will discuss the Poisson ratio. It is the relation between the contraction and the elongation of the isotropic material. What is Poisson ratio? This is the ratio of lateral contraction to longitudinal elongation is called Poisson ratio. It is the lateral contraction, it is mu, and the longitudinal elongation, lambda. So the relation between the mu and the lambda is called Poisson ratio. In the last class, we have studied that the relation between elastic constants Q, N, K. In this, a cube-shaped isotropic material was selected, and three different stresses P, Q, R are applied perpendicular to each other. The A, B, C, D, A, D, H, E, A, B, H, E, F are three stresses will produce the elongation. The extension is indicated by the symbol lambda, and the contraction and the compression is indicated by the symbol mu. Along other two, if a extension is produced in one direction, automatically in the other two directions the compression will be produced. So it is a cube-shaped isotropic material. We have three types of stress: P in this direction, Q in this direction, and R in this direction was applied. So due to the stresses applied on this cube, a lateral contraction and a longitudinal elongation is obtained. So it is the ratio between lateral contraction to the longitudinal elongation. It is called the Poisson ratio. Next we go to the expression for the Poisson. Derive the expression for Poisson ratio in terms of elastic constants. Well, we know what is elastic constant. They are the Young's modulus Q, rigidity modulus N, and the bulk modulus K is called the elastic constants. Already we have derived the lambda. What is lambda? Lambda is the elongation. Elongation is equal to 1 by Q. Q is the Young's modulus. And also the lambda plus mu. It is lambda is elongation. Lambda is elongation and mu is the contraction. So lambda plus mu is equal to 1 by 2n, where n is the rigidity modulus. So divide this equation 2 by equation 1. You get it is 1 plus mu by lambda is equal to q by 2n. And then on simplifying, we get sigma is equal to q by 2n minus 1. So it is the expression for the Poisson ratio in terms of elastic constant. So we have derived the Poisson ratio sigma. The symbol of Poisson ratio is sigma from the elastic constants. Q is the Young's modulus and N is the rigidity modulus. So we have derived the Poisson ratio in terms of the two elastic constants, Young's modulus and rigidity modulus. So it is the final expression for the Poisson ratio. Sigma is equal to q by 2n minus 1. And the next question is derive the expression for work done in stretching. So stretching, how much of force must be applied for the stretching. So it is known as the work done, the external force, the external work applied for the stretching of the elastic materials. So consider a body of length capital L and a force capital F acts on the body of the area of cross section A. So the body has a length capital L and the area of cross section capital A, and the force applied on the body is F. So on applying force on the body, the length of the body increases. So the length increases is L. We know well that what is Young's modulus? Young's modulus is the physical property of the material. It is indicated by the symbol Q. So Q is equal to longitudinal stress divided by longitudinal strain. We already studied longitudinal stress. Stress is nothing but a force applied on the area of the body. The force divided by area. What is strain? The change in length divided by original length. The change in length is due to the force. The change in length is due to the force applied on the body. So the longitudinal stress is equal to force by area, and longitudinal strain is equal to change in length by original length. So we get the equation Fl by area into change in length. So from this, it is the force. Now we are taking the force equation. The force is equal to QAL divided by capital L. So work done on what is producing a stretching to the amount dl. So the force applied, the work done on the body to stretch from the length capital L to dl. So the dl amount of length is extended, increased due to the application of the force on the body. So the work is equal to force into distance. So it is a force. dl is the distance, the change in length. So work done equal to force into dl. We already derived the expression for the force QAL by L. So work done is equal to QA small l by capital L into dl. So the total work done to produce a stretching of wire from the limit 0 to L. And if there is no force applied, the stretching is 0. On applying the force, it extends to the length small l. So we are integrating. So integrating from lower limit 0 to upper limit L. So we know that expression for F, substitute the value of F here. W is equal to QAL integral 0 to small l into L into dl. On simplifying, we have W is QAL integral L into dl is L square by 2. So on simplifying QAL L into L, we know that QAL into L is nothing but a force. QA small l divided by capital L is nothing but capital F. See here, QA small l into capital L is nothing but a force. So W is equal to half into force into L. So work done, W is equal to half into force into elongation. So L is the elongation. Now on taking the volume of the wire, already we have taken the area. Now we are considering the volume of the wire. What is volume? The area into length. Already we have derived the work done expression W of force divided by area into length. Now we are multiplying with length. So we get of force by area small l by capital L of force length divided by area into capital L. So 1 by 2 is taken here. Force by area small l by divided by capital L. So work done W is equal to half into force by area L by L. It is nothing but force by area is nothing but stress. Change in length by original length is strain. So the work done in stretching a wire is equal to half into stress into strain. It is the final expression for the work done in stretching a wire. So work done in stretching a wire is equal to half into stress into strain.